Okay, so I think the recording is now in progress. Is that right?
Yes.
Okay, thank you. Good. So then, so one more thing, of course, I have to say from the very beginning that the talk, at least the second part, will be based on the joint work with Martino Lanini and Alexander Putz. But for today, I'll probably not be able to say anything about this part from the paper, but I'll try to describe the some results from the theory of totally non-negative Grassmannians, and this is going to be based mostly on the works of Postnikov. But let me also mention the overview of LAM. And well, there are, of course, many other papers on this subject. Okay, and maybe one more thing to say, that there are some people present in the audience. So if you want to ask anything, please ask at any point. So your questions are very appreciated. Okay, so let me start from the very definition. So we fix numbers n and k. So n greater than 0, and then k between 0 and n. And of course, we all know that there is this Grassmannian Kn. So this is the classical Grassmannian. And what's going to be important for us? So the Looker embedding. So this sits inside the projective space of lambda k of Cn. Or, well, I don't want the C here. So should be some field. So let me put this k here. So k might be R or C. So whatever you prefer, of course, the usual thing is to work, well, I mean, it depends on what problem you are solving, but more kind of general setup is working with complex case. But what we are going to do here is the real case. So for us, this field is going to be the field of real numbers. And then, so in lambda k of, well, I should put here n, yes, of r to the n. So we have Looker coordinates. So these are xi, where I is going to be a subset inside the set n. So let me fix this notation. So this is going to be the set of numbers from 1 up to n. So the cardinality of I is going to be k. So, well, this is very standard, but let me fix the notation from the very beginning. So we have basis, say v1 up to vn is the basis of our r to the n. And so these xi, so they are dual to the standard Verge products. So ei1 Verge eik, oops, these are v. And so the i's are, well, just these numbers, say, in the increasing order. So these are my Looker coordinates. And then, so this means that since we have an embedding of the Grassmannian Kn into this projective space, so each element, each point hex from the Grassman variety has, or maybe I should use another letter. Each point, say, well, L, has coordinates. So these are x, I of L. And this is nothing but the coordinates of the point corresponding to this L with respect to the Plucker embedding. So in other words, we can represent L via the collection of Plucker coordinates. And of course, these numbers are not arbitrary numbers. They are remark. So x, I of L are subject to quadratic Plucker relations. To quadratic Plucker relations. However, what's important for us at the moment that these are some numbers. So any questions so far? Okay, so once again, let me repeat that your questions are very much appreciated. So please feel free to ask at any point. Okay, so now the definition. So the totally non-negative Grassmannian so denoted by gr Kn greater than 0, so is a subset of the Grassmannian. So let me stress that this happens over R, so over the real numbers. Consisting of points L such that all the Plucker coordinates x, I, L are, well, of the same sign, but let me write that they are non-negative. Of course, so these are coordinates in projective space. Therefore, you can freely multiply by one number. I mean, all the coordinates by one given number. So you can, of course, multiply them all by -1, getting them all non-positive. But what I mean that just they have to be of the one of the same size, of the same sign. Okay. So this is the definition. Let me give you an example. So the example say let n equals 3 or even 2 and k is 1, and then we are considering the points. So the Plucker coordinates are just coordinates. So we have projective line, so x1, x2, and we want both x1 and x2 to be non-negative. So, well, of course, this is well, there are many reasons why one is interested in these objects. So, for example, so let me put this as a remark. so this remark is actually very important because it provides link to Lustig general definition. I mean, general for not necessarily for Grassmannian, but for other flag varieties, for example, complete flag variety and so on. So I mean, so this link is provided by the non-negative part of the group GLN. And so these are matrices with matrices with non-negative minors. And the importance, well, this group is important because it acts, one can show that it acts on the TNN Grassmannian. And well, actually you can use similar technique to define the action on an arbitrary flag variety, partial flag variety, and then proceed with the general case.
Why is it a group?
Say again?
Why is it a group?
No, I'm sorry. It's not a group, it's monoid. Yeah, so it means that the product of two such things is again is similar things. So actually there is a theorem due to Loebner-Whitney saying that this group is generated by the following matrices. And then A. And also where here the A here is non-negative, and the stars here are also non-negative, but positive actually. So you can multiply, but so this is not a group. However, you can still consider the action, and you consider the orbit, and so this is the setup. So actually, it's not evident that this monoid acts on the totally non-negative Grassmannian, but you can show that. Okay. And actually, so why do we care? So maybe the important thing is that this kind of slogan, so this TNN Grassmannians have a very rich combinatorics. And actually, well, this combinatorics we are going to be interested in comes from topological structures. So from cellular decomposition, I'll get there in a minute. But let me repeat once again. So this positivity phenomenon, they are very popular these days. And so there are many reasons why one is interested in these objects, but for us, the importance is going to come from the decomposition of these Grassmannians into cells.
May I ask?
Sure, absolutely.
Is it true that, or not true, that you can, that it is enough to have positivity just for some subset of X types, not for all X? Like for a seed.
Yes. So by the way, can the online participants hear the questions asked by the offline participants?
Yeah.
So you
I can hear it. Yeah.
Okay, thanks, Shin. So yeah, so indeed, so this is the very good question, and so there are some special. So you don't have to check the positivity for everything, but you can do this for something. Well, some people call this, I think, bases or seeds. I actually don't remember, but I cannot formulate right now what is the kind of minimal set to be checked, but you're absolutely right. So it's a good question. Maybe Igor can say something. No?
I just want to make sure I understood the question. So the minimal set of coordinates that you positive for the rest of the
So the minimal
I
number,
don't know.
the minimal number of minors, or the minimal number of
Minimal
Pluker,
sets.
or Pluker coordinates, or
Definitely there are negative values, minimal sets that have this problem. No, I don't know.
So
Yes.
maybe I can give some quick remark.
Yes, please,
So maybe you just take a cluster algebra structure and you take a cluster. This will give you the total positivity test. So for example, you take maybe later you will talk about Prabby graphs. You take all these Pluker coordinates arising from this Prabby graph. They will give you a totally positive test.
Mm-hmm.
And for this, if you take the GLN, this big one, you take this Lohner-Whitney decomposition, and this is give you exactly the total positivity test. You take the double reduced words and something like that.
Mm-hmm. Thanks, Shin. Mm-hmm. Okay, so then let me give you an example of the decomposition we are going to be interested in. So we consider an example. So let again n be 2, k is 1, and then we take the Grassmannian 1, 2, the total non-negative Grassmannian, and then so how can we decompose it? So, well, we can first take 0.10, just a point, and then we can take a 0.01. Actually, let me do the following. So let me write this point as a 0, a strictly positive, and then here I put 0a. So a strictly positive. So of course these two sets are points, but let me so far write like that, and then finally we have a, b, with both a and b being strictly positive. So why do I want such a decomposition? So first of all, of course, so this is nothing but point, and the last thing, and then the last thing is the most interesting one. So this is r greater than 0, just to the first power, so just r greater than 0. And so maybe to illustrate it better, let me consider the case GUR 1c. And this is the union of 7 sets. So the sets are 1, 0, 0, 0, 1, 0, and 0, 0, 1. So these are 3 of them. And then we also have, and I put again here A, and A. And then I put G. A. So I put A, B, 0. like this, and then 0 AB, and then A0B, and then finally have ABC. So you see all those guys are here strictly positive. So this turns out to be just point, and then 3 times R greater than 0, and then 1 time R greater than 0 squared. Okay. Good. So you can see that we decompose our Grassmannian into the cells, but please keep in mind that these cells are positive numbers into some power. Okay. So actually, this is related to sorry. Sorry, just 1 second. So something is wrong with the editor. Oops. Okay, now it works. Good. So there is a theorem by Postnikov. Saying that the Grassmannian Kn greater than 0 admits decomposition into the cells of the form R greater than 0 to some number S. And now the question is, what is the labeling set for these cells? And these are the so-called positroids. So what are the positroids? So let us, so for L in the Grassmannian, so let us denote by ML, so the set of such I in NK. So I are collections of K element subsets of the set from 1 to N. So these I, they have to satisfy the condition that Xi of L is strictly positive. So remember, we defined the Grassmannian as the set of points where all the coordinates are non-negative, and then we choose the sets where the coordinates are positive. And okay, so by definition, this ML is a subset formed by K element subsets of 1 to the N. And then the claim is that, which is not going to be too important for us for today, the claim is that ML is a matroid So again, we're not going to use this, but a matroid is a collection of subsets of cardinality k subject to some condition. Okay, maybe why don't I write it? So matroid, i.e., for any I, j inside M, L, so and I from I, there exists a j from j such that I minus I union with j is again in M, in ML. So this is the definition of a matroid. And then a positroid is a special case of a matroid. But let me add one more remark. So one can ask a similar question. About complex Grassmannian. So, well, I mean, one can ask what are the set of Plucker relations such that you can find a point in a Grassmannian with exactly those set of Plucker coordinates being non-zero. And then this is, there is a famous paper by Gilfand, Gareski, McPherson, Serganova. Well, treating this question, but the conclusion is that the question is very complicated and the structure is very complicated, and actually there's not too much which can be said here. And what is very nice about this non-negative story is that positroids can be described in many explicit ways.
What does negative do?
Say it again?
What does negative do?
I mean that, so you consider now the points in the Grassmannian such that they correspond to some non-negative Grassmannian points. Yes, so I mean, the general question is about the complex or real Grassmannian, but then you can ask what are the Gilfand, Gareski, McPherson, Serganova strata that correspond to some points in the non-negative Grassmannian.
What does the non-negative for complex?
I'm sorry.
Like, so this is
Yeah.
this is the real Grassmannian.
Yeah.
And of the Gilfand-Serganova strata, like, how does this Gilfand-Serganova stratification in the complex Grassmannian correspond to the Gilfand-Serganova stratification of the real Grassmannian?
Yeah, but you can ask.
Is there the same?
They're the same. Yeah. The same. Yeah.
But and how many of them intersect the negative Grassmannian?
Well, I'll say this in a minute. Yeah. So actually, this is about the description of the positroids. So we wonder what are actually the positroids and how to describe them. Okay. So any questions so far? Okay. So if no questions, then let me proceed. So so there are many ways to describe the positroids, but before the description, let me actually give somehow more concrete formulation of the theorem of Postnikov, namely, so come on, what's happening? Okay. So more concrete formulation. Of the theorem of Postnikov. So I mean, suppose, so let me denote by PKN be the set of positroids. And for M being a positroid, so let pi M positive be the set of such L in the Grassmannian Kn greater than 0, such that ML equals M. Okay, so what I'm doing, so I just take those points in the Grassmannian such that the corresponding positroid is exactly the one I fixed from the very beginning, M. And then it's a kind of continuation of the Postnikov theorem, says that P M positive is isomorphic to R greater than 0 into some power S for some S. Okay, and then this is, well, we can get back to our example. So if N is 3 and K is 1, when we've seen that actually there are 7 positroids, and actually these are 1, 2, 3, 1, 2, 1, 3, and 2, 3. Oh, and 1, 2, 3. Yeah. So actually, this is a which can be easily generalized to an arbitrary n case, and k is still 1. So for k being 1 and arbitrary, so the positroids are just non-empty subsets of 1 to n. So this just means here that you can find for any set of coordinates, you can find a point in the projective space with this set of coordinates being non-zero, with exactly this set of coordinates being non-zero, and this actually very clear. So the question is how now to, so there's a question, how to label the positroids. So this is the first question, and the second question is, what are the dimensions of cells by M positive for M being a positroid? So this can be rephrased, well, in some sense, so we are interested in Euler characteristics. And Poincare polynomials. So this is the kind of our point of interest. Okay, and so so there are many, as I said, there are many objects parameterizing the positroids. But before I go there, let me give you a couple of numerical examples. So let n be, say, 4 and k is 1. Then the corresponding Poincare polynomial is q to the 4 plus 4 q cubed plus 10 q squared plus 4 q plus 4. Oops, sorry. No, I wrote it wrong. Sorry. So q to the 4, q cubed actually, because the dimension is 3 here. Plus 4 q squared plus 6q 4. So what does it mean? It means that if we consider the Grassmannian on 4 greater or equal than 0. So this is just the projective three-dimensional space greater or equal than 0. And then the corresponding decomposition is it has one three-dimensional cell. So actually, for example, this three-dimensional cell is nothing but A, B, C, D, all A, B, C, D being positive. Well, and then, so of course there are 4 parameters here, but since we are interested in the projective space, there are actually 3. So this is q cubed, and then 4q squared, 6q, and 4, and you can easily find, well, see that these are binomial coefficients, and actually this case is very simple, but more, oops. Absolutely, yeah. So just the meaning, so maybe I should put it quotes. But you can define the Euler characteristic of Poincare polynomial saying that this is the number of cells of given dimension. But of course, you are absolutely right. This is not what we usually mean by that. Okay, and then maybe one more example is Grassmannian 2, 4. And then these numbers are q to the 4 plus 4q cubed plus 10q squared plus 12q plus 6. So you can see that these numbers are somehow complicated, but well, you can compute them, and there is a paper by Lauren Williams, computing these coefficients. Okay, so now how to describe the positroids. So the most the most important and the most conceptual way for us is the notion of the so-called Grasman necklaces. So let me give the definition. So a Grasman necklace so this is a collection of sets I1, IN. So each AI being a k-element subset of the set 1 to n. So A from 1 to n. And there is a condition saying that such that I A sits inside I A plus 1 union with A. So what does it say here? For example, I1 sits in I2 with 1, and I up to IN sitting in I1 union with it. So you can see that the condition says that more or less I1 is a subset of I2, but this would be very boring because they are all of cardinality k. So therefore, if one sits inside another, they should be equal. But the condition says that there is some special number, say 1 here, such that the number 1 might be contained in I1, but not in I2. And the last condition is, well, kind of similar, but we have n as this special number. So what's important that there is this cyclic object here, and this we are going to utilize later. Okay, so for example, if n is 2 and k is 1, then so there are 3 Grasman necklaces. They are so I1 is 1, I2 is 1. That's the first one. The second one is I1 is 2 and I2 is 2. And the last one is I1 is 1, I2 is 2. So the second one is the third one is the most interesting. You can see that neither I1 sits in I2 or I2 sits in I1, but if you use the condition we actually have, then this is okay. And so let us denote by Grasman necklace Kn, Gn, Kn be the set of Grasman necklaces. Of course, we have to fix the numbers k and n in order to define the set. So we always assume that they are fixed. Okay, and then so the proposition so it says that there is a bijection between pkn and gnkn. So the Grasman necklaces, they label the positroids, and actually there is an explicit map, at least in one direction. So for that, we'll use one more notion, which is going to be important. So this is an order. So in order, partial order. Order on GNKN. So, well, let us say that first of all, we introduce an order, several orders on numbers. So we say that A less than A plus 1, less A plus 2, so on, up to A minus 1. So these are n different orders on the set n. So this order depends on the number A. and A here from 1 to n. So they are kind of all very similar, but the question is where you start. And okay, and then after that, so given, so maybe let me write the definition. So we say that for two elements, I1, IA, IN, and J1, JN, two elements from the Grasman necklaces, we say I less or equal than J if for any A, IA less or equal than JA. So is it clear what does this mean? So shall I comment on that? Zhenya, shall I say something? So I just mean that, so we've defined, oops, first of all, I have to put A here. So I, I defined orders. So we have orders A on N. And here I'm comparing two K element subsets, but this is done just by minimal element. Yeah, so we go from minimal to the maximum and compare.
Like a code.
Yes. So in other words, so if we have I being I1, IK, and J being J1, JK. So we say that I, and then we have an order. Then we say that I is less or equal than J if and only if I alpha, oops, less or equal than J alpha, where here we order I1, IK, and then J1.
Well, even capital I and capital J, it can be capital I A and the capital J, A can be comparable.
So we in order to say that one Grassman necklace is less or equal to the other Grassman necklace, yes, this condition, we ask that IA is less than equal than JA with respect to the order eighth order.
And this order is also the order.
It's a partial order. Yes, absolutely. Yes. So of course, so this is a very restrictive condition, and not any two K tuples may be compared.
So what is quantifier for all alpha?
Here, yes, absolutely. Thank you. So here for all alpha from 1 to K. And let me stress once again that this order here, so should be fixed. Yes. So I mean, this order is different for different IAs and JAs. Yes. So maybe an example could be useful here. So the minimal Grasman necklace is the following. I1 is 1K, I2 is 2K plus 1, etc. up to in is well, where should I start? Probably I should start with n, right? And then proceed with 1 up to k minus 1. Right? So this is the minimal Grasman necklace because I1 is the smallest possible thing in the order 1, I2 is the smallest possible thing in the order 2, and so on. Okay, good. And then so the proposition says that if you have an element M in the set of positroids, then you can attach to M the Grasman necklace I of M, which is I1 up to In, where IA is minimal element with respect to the 8th order of all the sets I in M. Okay, so this means that in order to get, so the proposition said that defines a bijection from PKN to GN. So there is a bijection which is defined by taking just minimal elements in the positroids. Okay, and so this is the one possible way to label the positroids, and actually there are several other ways. But before I go further, let me actually give you one more. So of course there is a question. So what is the dimension of the cell corresponding to a Grasman necklace? Well, and then we'll get here later. But before I proceed, I want to give you probably the most famous. So these Grasman necklaces, they are also very famous, but there is another simpler, or kind of in a sense, more natural objects parameterizing these positroids. Well, we are not going to use it, but anyway, let me give you the definition in order to somehow make a connection with the general theory and with the general Lustick's approach. So these are the so-called L. So this is the symbol kind of reverse L diagrams. So these objects are easy to formulate and easy to state, but maybe not that easy to prove. Probably this was the first kind of step made by Postnikov. So this is called the Lie diagrams. And the reason is that there is this letter L, which is somehow goes in an opposite order. Maybe, by the way, I have to write here like this. Oh, I didn't succeed. So I mean, there is no this additional segment, and maybe I better erase this segment here as well. You'll see why in a minute. But the reason is that you kind of have to flip this letter L, and what you get is Li or Le. I don't know. Okay, so what is that? So we still have our favorite numbers, K and N, fixed. And then you consider the box rectangle k by n minus k. So of course we are used to these pictures in the theory of sure polynomials, Grassman varieties, Grassmannians, and so on. And then you consider a Young diagram. So let me draw it here. Oh, maybe I should like this. Something sort, for example, 4 rows and many columns. Okay, so this is a Young diagram fitting inside k times n minus k. Maybe even let me make the box larger. And this is k, and this is n minus k. And inside we have some diagram. Okay, and Lie diagram is a Young diagram. So lambda is a partition. So for example, here my lambda is 4, 5, 6, 7, 8, 9, and then 3, 7, and 7 again, and then 4 and 2. And then I take the corresponding Young diagram and then insert 0 and 1 in the boxes with the only condition. The condition is that if you have a 0, then this is not allowed. So such a pattern not allowed. So that's it. So we inside our picture, so inside our Young diagram filled with numbers 0 and 1. Well, you can fill in any way you want. The only thing you're not allowed is to put 2 ones, one to the left of a 0 and one kind of in the box which is right upstairs. Okay, so this is the condition, and then well, you can see the object is somehow very easy to define.
So you correctly understand that the form is 0 and 1 and the infinity.
No other conditions. So you just put 0 or 1, and the only condition is that you don't have such a pattern. So 0. So there are 3 elements, 1, 0, and 2 ones. So you cannot have, let me put it here. So this forbidden thing, 0, 1, 1 is no good. But otherwise, you can do whatever you want. Okay, and then the theorem, again, due to Postnikov. So the theorem says that these Lie diagrams label the positroids, so they're in one-to-one correspondence. Moreover, the dimension of the corresponding positroid cell is equal to the number of ones in the diagram. So you see, this is an object, which is why actually I decided to give you this definition, because first of all, it's very easy to formulate. Second, there is a very explicit description of the dimension of the cell. And third, of course, you can well recognize this k times n minus k rectangle part of a matrix. Well, I mean, if you have a matrix, so we all know that the Grassmannians are somehow controlled by these k by n minus k matrices, and this was the Postnikov's approach somehow to construct an analog of Gram-Schmidt process and to determine the cells in terms of these diagrams. Well, there is this funny combinatorial rule with this L flipped condition, but otherwise this is somehow very concrete. Okay, so so again an example. So of course there is one Lie diagram with k times n minus k units. So you just take the whole rectangle and put ones everywhere. Okay, and also this one thing, and also another important thing that there are many Lie diagrams with no units at all. Yes, because so you take any Young diagram fitting inside the rectangle k times n minus k, and then you put all zeros everywhere, and so that's it. So actually there are these binomial coefficient of these diagrams, each giving you a zero-dimensional cell. Okay, so good. Well, this is our example.
You're not describing the equation.
Say it again.
You are not describing the equation.
No. And actually, this bijection is, so the price to pay for the easy definition is the complicated bijection.
Like for instance, you can take any Lie diagram, right? And you can fill out the rest of the rectangle with zeros, and it's also a Lie diagram. And like these are different Lie diagrams, they define different positives. No. Oh, okay. But you no, you cannot fill out their zeros. There's a question. Can I ask a question?
Sure.
I wanted to ask it for a while.
Sure.
It goes back to the injection in the necklaces and positives.
Yes, let's go there.
What's the, maybe I'm missing something obvious, but what's the inverse?
No, you that's a good point, but I don't know a simple formulation. So I'm not sure there is an easy way to say how to construct a positron starting from Grasman necklace. Maybe there is a way, but I'm not aware about this.
So the elements of the necklace are the minimal. So you have to take like, doesn't contain all of the elements of the necklace and something else. Is that how it works?
Yeah. Sure.
Take the whole necklace and add some other.
Yeah. Sure. Yeah, because so you see the map. So minimal means that at least these guys, they have to be there, right? But you have to take something else.
I mean, you don't have to take I sub A and then take everything larger than I sub A. That's not correct. With respect to less than because that fairly straightforward.
I think not, but I'm not completely sure. But I think not. Okay. So any other questions? Okay, then let me maybe let me add one more object, which is due to maybe before that, let me add one more remark saying that there is a natural partial order on the set of positroids. So I mean that this order, so coming from the closure relation. So I mean we've defined these positroids as some data labeling subsets of the T and N Grassmannians, and then we can take the closures of the corresponding set, looking at those smaller cells living inside these closures. For example, we have this, say, n equals 3, k equals 1 case, and then we had this positroid cell ABC with A, B, C being positive, and this cell is a kind of open, so meaning that the closure contains everything. Well, for example, there are kind of nearest guys in the closure, 0, 0, A, let B, C, and A, 0, C. And then you go further, so there is an order here. And then we've also defined an order on the set of Grasman necklaces. And then one more proposition says that the bijection between positroids and Grasman necklaces is order reversing. So as an example, well, we can say that there is a maximal positroid cell. So actually this positroid cell consists of all possible k element subsets. So of course it's not complicated to construct a point in the Grassmannians such that all coordinates are non-zero, all of them are positive. And but also there is a minimal Grasman necklace. Actually, we've mentioned it above. So, well, it's important to note that the order is somehow reversed order. Okay. So this is one remark. And now let me introduce one more parameterization. Actually, this is more or less the same, but it's going to be somehow useful for us. This is called juggling patterns. And then you can guess at least one author of this name. So there is one famous mathematician who is very famous not only because of this mathematics, but also because of his he is a juggler, very professional juggler. So this Alim Knudsen. And also in the paper with Lam and Speyer. So this is the paper on positroid varieties and on positroid cells, and they define these juggling patterns. And actually, this is kind of very close to Grasman necklaces. Namely, we again consider. So we consider the elements, say J1, Jn, and Ja be an element in Nk. So this again a K element subset of the set consisting of n elements from 1 to n. And well, we say that this J1 Jn is a juggling pattern. If Ja sits inside Ja plus 1 union with n for any a. So actually, you see what's the difference between the Grasman necklaces and juggling patterns, that here we are using one single n for all a, while for Grasman necklaces, we were using different numbers for different j's or i's there. Well, it's easy to see that this is more or less the same, but why did I draw that? Did I give you this additional definition? So maybe I should say, of course, that so there is a bit bijection, an easy bijection. Bijection between Grasman necklaces and juggling patterns.
Because these juggling patterns, they are very simple, right? Once one of the elements contains n, they are constants. So
Yes, yes, but so actually you see that these Grasman necklaces, they are simple in the same way. So I mean, either either you are kind of the two sets are either equal or differ by one element. So this only kind of the matter of reparameterization. So whatever, so you just, instead of choosing n different elements here, you choose one n. So you kind of shift. So to move from Grasman necklace to juggling pattern, you just subtract something or add something. So maybe let me give you a picture, because so actually this picture probably illustrates something on combinatorial side, but it will also be useful for us from the point of view of quiver Grassmannians. And the picture is as follows. So first, Grasman necklaces. So I take, say, an example, n equals, say, 5, and then I put the 5 dots representing the numbers from 1 to 5. And then since I have I1, I2, I3, I5, I draw 5 times these dots. So actually I'm going to write here I1, 2, 3, 5. And so these are the subsets here. And then I put here numbers 1, 2, 3, 4, 5. So meaning that I have 5 times columns consisting of numbers from 1 to 5. And then inside these numbers, I'm going to find I1, I2, I3, I4, I5, and K here, say 2 or whatever. But what I do care about, so let me draw this picture. So I put segments here, I put segments here, I put segments here, I put them here, and then I also put them here, and also I go backwards, and then I go backwards here, but not at the last place. So just what I mean that we have a, you see, we have a no segment between, maybe I could here across. So I don't have a segment here, not here, not here, not here, and actually also not here. So meaning that I don't go backwards. So the I1, I2, I3, I4, I5, so they are kind of, so let me, for example, say K is 2. And then I can choose I1 to be, say, 1 and 3. And then since I have 3, this 3 goes all the way here. But this 1 does not have to be contained in I2. It can be there, but not necessarily. And then I can put cross here, meaning that I2 is 2, 3. And then again, this 2 does not go too far. But in principle, it can go somewhere. So I mean, I have to choose an element here. And then, for example, I can choose it, say, here. And then I choose here. And then, for example, I go backwards here and see. Okay, so maybe I better circle them. So the circled points are exactly the elements of my sets I, and you see the crosses mean that you don't have to follow the path if you pass from IA to IA plus 1. And just to finish, let me draw a similar picture for J's. So actually, this is very, very similar. And the picture here is just, so I go this, like this, like this. Here, here, and that's it. So this is the pictures, and so these are juggling patterns. So juggling patterns and Grasman necklaces. Okay, so probably that's it for today. And so if you have any question, if you have questions, please ask. And once again, very sorry for technical problems. So please, if you have any questions.
Like what I was trying to ask.
Yep.
Is that whether so when I asked about the Sagano strata, I meant so how many of the Gelfand Sagano strata sort of fall into the positive or the negative. So how common is it for Sagano straight?
So you want some information about the function regarding
I
the
want to
structure, yeah?
compare the number of the strata and
This I don't know.
but actually, I guess you're gonna say next time, but these strata, they are reducible, right? In the volume.
But these are just cells. So I mean, we kind of.
No, okay, they are,
So we're not considering the closures.
okay, but like, okay, is it a certification? Are you gonna talk about this?
No. No, but no, because you see, it's not a kind of. So in order to talk about certification, you probably better consider the complex case, and these are the so-called positroid varieties. But I don't know if people consider the closures in the real case. I'm not sure.
But they are not reducible, and it's not a certification, neither of these.
So I mean for the positroid case or what?
For the real non-covalent negative.
It is. So I mean you have this closure. Yeah, but you see the problem is that it's kind of so I mean the varieties. So these are not you can't use the algebraic geometry here to describe this totally non-negative thing, because so you have so these are rather topological maybe, but
Well, it's a real.
yeah. But for so there is an object in complex geometry. These are called positroid varieties, and you take the closures of this kind of positroid part and then work there, and they are nice.
And in the complex, these complex things, they are intersections of Gelfand-Sergano strata with something. Why I'm asking is because the Gelfand-Sergano strata, they are notoriously very.
Yes,
They notoriously don't have any nice properties.
that's true. But here, if you restrict yourself to the positroids, not all the matroids, but only on the positroids, then they are much better.
And in the complex case,
Yes.
you can also.
Yes. So further questions? Okay, so if not, thank you very much, and let's stop now. So I'll continue next time. I hope we'll get less technical problems.
Let's end the speaker.
Yeah, thank you and bye-bye.